So, now what is now this is what closed immersion or locally closed immersion. Now, what I want to talk about fiber product of pre-varieties. This is extremely important topic in algebraic geometry. This makes the subject much richer than any other. This fiber. Yes, they are all they are. This is the most general object in that sense. There are particular cases you will see. Fiber product. These are all particular cases. So, what I want to talk about, suppose x, y pre-variety. So, we already know that x cross y is a pre-variety. So, you basically you do it for the affine and then glue them together, and gluing information coming from x and gluing information coming from y. So, now uy, so x is covered by uy, y is covered by vj. Then you consider uy cross vj for affine, if the product is tensor product, then you somehow you glue it and then you consider. That's the idea. Okay. So, I am not going into proof of that, but this one thing to notice that it is not the product topology. The topology on the this product variety is much finer. Okay. So, and it has the universal property that if I have, so you have this projection map from x to y, and then if you have some map here, then it factors through, then you can define r comma s, right. This map makes sense. So, this diagram comes. Every z, if you have a map from x and z to a map from y, then the set theoretic map, this is a morphism. So, if I call this gamma is a morphism. That is the hardest part, to say that this is a morphism. This diagram commits. So, it has a universal property. Okay. So, now suppose I want to change a little bit first. I want to talk about graph of a morphism. So, if you start with a morphism A from x to y of pre-varieties, then you consider so you have product x cross y, which is a pre-variety. You define this map, say j of f, x going to x comma f of x. First of all, this is a map of variety. This is a morphism of pre-varieties, because each projection, if you project to x and project to y, they are morphism. So, it is a morphism of variety. Now, you call the gamma of f is image of j of f, which is a sub in here in x cross y. First of all, jf is injective. Okay. So, the point is that the proposition this jf is a locally closed immersion. So, that means image of jf is a locally closed subset of x cross y. Is it clear what I am saying? So, jf is a map from x cross y is a locally closed immersion. For any morphism of pre-variety. Okay, and as a corollary, you see, I leave this again for the tutorial session. I leave this as exercise. You try to prove that this is a locally closed immersion, and so that means what? That means image. So, first of all, this is isomorphism is not very difficult to say. This is not very. So, now this you have to say that this inclusion map is a locally closed subset, right? This map is injective because x is going to the graph of x comma fx, right? And this is isomorphism and this is a locally closed subset. So now as a corollary you see that the fiber product exists. So as a corollary, so you define, suppose, so the corollary is that the category of pre-variety is fiber product. So what is a fiber product? So what I want some object x cross y z. So this is a set, but set theoretically it is nothing but f of x equal to g of y, where f and x are two maps from x to z and g is a map from y to z. So you define as a set x cross y, the fiber product of x and y is a set of all points of x and y, x, y such that fx equal to gy. The point is that this is a, of course, this is a sub of x cross y. Now, point is that this is a locally closed subset of x cross y. Because of this above, I will explain why. This is a locally closed subset of x cross y, and being a locally closed subset gives automatically a variety structure. So that's how you get a variety structure on the fiber product. And this fiber product also, it has the universal property. That means if you have a map T to x and T to y, then you have a map, unique map. So basically this is the projection map P1 and P2. That whenever you have map R and S, then you can define this gamma always is nothing but R comma S. This map is a morphism. You know it goes to the product, but why it should be in the, it's a morphism of variety between these two. So that requires proof, but that is also true. So it has the universal property. So whenever you have a map of diagram such that this commutes, then you have a map to the fiber product. Okay. So let's prove this fact. So call this W x y, which is x cross f of x equal to g of y. So this is a locally closed subset of x cross y, and it has the desired universal property. Desired universal property means what I just explained. Whenever you have such this is f, this is g. Whenever you have a map of diagram commutative, then it should it factors through this. The proof is, so you consider the map H from x cross y to z cross z. So x comma y goes to fx comma gy. Now what is the fiber product W as a set? This is nothing but H inverse of delta z. Right? Now delta z, now this map is a locally closed immersion, is a locally closed subset. So inverse image of, and this is a morphism. So inverse image of locally closed is locally closed. Right. So then W is a locally closed subset of x cross y. But x cross y is a pre-variety. So locally closed subset of a pre-variety is a pre-variety. So that's how you get a pre-variety structure on W, right? So this is your x cross y. Z, right? H inverse of W. Huh? Delta, just that we saw, right? I just gave a exercise. I did not give exercise. AJ, F is a map from X to Y. Then this map X to X cross Y. You take F to be identity. If F is identity, then what is this? This is delta X. Right? Image is delta X. So image is a locally. So this graph is a locally closed subset. So in particular, if you take F to be identity, then it is a so hence fiber product is a pre-variety. Now I leave it to you to check that it has the universal property. It requires some work. I leave it as exercise. Show that. Show that it has the required universal property. And here you need to use another exercise. I'll just write down that hint or exercise. That when something is a locally closed immersion, suppose you have a map, say X to Y, and G is a map from Z to Y. When you have a map from H, this such that so okay, let me write. That if it is a morphism of it is a locally closed immersion, and G is any morphism of pre-varieties. These are all pre-varieties. And suppose you have a map. Oh, okay. Sorry, not sorry. Okay. Sorry. Suppose G is a map from Z to Y. Then there exists a map from H from Z to X such that H from Z to X such that H G composition H, or no, sorry, Z to X, so this is X to F composition H is equal to G if and only if G of Z is as a set F of X. So what it is saying, that suppose you have a locally closed immersion, okay? So let's write it like this, that suppose X to Y, this is a locally closed immersion. This is a locally closed immersion. So locally closed immersion I can think as this is a locally closed subset basically. So you say X to Y is a locally closed subset and Z to Y is there is a map. Then when it lifts to a map from X to Z, so this is H. So this is your F. I would have been a better notation. So if and only there is a map from X to Z, the map is very clearly, you can define So when if it has a map from X to Z H, if and only if that you take the image of X in Y and image of Z in Y, they has to be there. So GZ has to be inside f of X. Then you can define a map uniquely. So this is the hint, and probably this also requires some proof. So I leave it as exercise again. So you have to use this to prove the universality. It will not come free, but I just leave it here. I'll discuss this in a tutorial session. Okay. Okay. So this is what, so fiber product. So right. So now few remarks. So some remark. That F is a morphism of pre-variety. And W is a locally closed subset of Y. Then F inverse of W, you can talk about F inverse of W as a set. This is nothing but W cross X over Y, where W is the inclusion map. Nice one. So in particular, when you take W is a point, then what is the F inverse of point? This is a fiber, right? This is the fiber product. So fibers you can think as a fiber product over the point, or fiber over a curve. Suppose W is a curve, closed curve. So then F inverse of C, this makes sense. And this is not, as a set is fine, but as a variety also it makes sense. It is a subvariety. Right. So this says that whenever you have some X to Y map, and if you take something here, sub-object, then F inverse Z makes sense, and F inverse Z is also a subvariety of X. So this map under restriction map, this is also a map of pre-varieties. Locally closed. Even for locally closed, you don't need closed. For a locally closed subset, also inverse image makes sense, and it has a pre-variety structure or pre-variety structure. So this is one remark, and the second remark. Okay. The other remarks I will make little later. I already defined, but let me define it again. When this so definition, X is a pre-variety and delta is a map from X to the diagonal map X cross X. X is called variety or separated if delta is closed. If separated pre-varieties are called varieties. So that's why when you in scheme theory book, if you read any scheme theory book, it says separated finite type K algebra. That's how you define variety. Separated finite type K scheme. Separated, reduced, some books they do that, yes. But in general, you can do it for pre-variety. Non-separated variety also you can talk about. Yes, analogous of Hausdorff. It is never Hausdorff because two open sets will always intersect. But you need to work on, you need some property like Hausdorffness. So this is analog of Hausdorffness. So criteria. So now whenever you put some condition, important condition, you ask whether there is any criteria for separatedness. Criteria. This makes life little easier. Because when you have something, suppose you have a point, suppose you have some map to say k or something. If you have a function, then or some objects, say not k, some objects, say y. Then by continuity, you know that this object cannot go to two points. See, for example, if you join two affine line under identity map, you get a object like this. But then if you take the puncture space a1 minus 0 to this, if x is this a1 union a1 with which is identified on this open subsets. So now this a1 minus 0, when you embed it into, you can embed it into x, but you don't know which. Now if you cannot complete this map. So this 0 you can go to either of these 2 points. That will make the map continuous. So this makes, so if it is separated, then it's not the case. So makes life little simpler. That is the reason why separatedness. So x is a pre-variety. So this is a proposition. X is a pre-variety, and it has open affine coupler. Open affine. Then x is separated if for all ij this OX of ui cross uj. So ui intersection ui is sitting inside ui cross uj, right? X is sitting inside x cross y. Uj is also sitting inside ui cross uj. So in particular, ui intersection uj is sitting inside ui cross uj. So there is a map OX ui cross uj to OX ui. This map is surjective for all ij. So OX of ui cross uj, this is isomorphic to OX of ui tensor OX of uj. These are all K algebra, so this is tensor over K. Right? If this map is surjective, then X is separated. Again, I leave it as exercise. I'll discuss this in tutorial session if you are. But this you take as assignment problem. So now after this, I make some remarks, important remarks. So X is a variety. X is a variety means it's a separated pre-variety. X is a variety and Y is a locally closed subset. Then Y is a variety. So now this will say, so once you know, if you prove that projective varieties are variety, then everything is taken care. Quasi-projective, quasi-affine, these are all varieties, right? So if you know projective varieties are varieties. So this is projective PNs are varieties. They are variety in this sense. That means it is a separated pre-variety. So, only thing you need to check the separatedness. So, F is a morphism of variety x to y. Then this map, the graph x to x cross y is a closed immersion. In particular, you know, for pre-variety, this is a locally closed, right? But when x is a variety, it's a closed immersion. Fiber product. So locally closed subset of variety is variety. So if you, so x cross y, if x is a variety, x cross y is a variety. If x and y are. So now that will say that locally, now you saw that that fiber product is a locally closed subset. Separateness, I just gave a criteria, right? Oh, for morphism of variety. Okay, okay. There is a condition which is when a morphism of variety. So what will be a natural way of? I'll come to that. Let me complete this. I'll come to that. That's a very good question. Yeah. Fourth is that intersection of affines are affine. So this is very important, that x is a variety, u and v are affine open, then u intersection v is affine. They will be open, but the point is that why, if you intersect two affine open subset, why that should be affine? That's not clear. That is true if x is a variety. Okay.